Hi everybody, I'm just going to do the last example from 2.6. We did the rest of 2.6 in class, but I didn't get to this last example, so I said I'd post a video. So here it is. So kinetic energy, K, is the energy due to motion. When an object is moving its kinetic energy, it's determined by the formula K V is equal to 0.5 mv squared, where K is measured in joules, m is the mass of the object in kilograms, and v is the velocity of the object in meters per second. So suppose we have a ball with a mass of 350 grams, and it's thrown vertically upwards with an initial velocity of 40 meters per second. Its velocity's function is determined by this, where t is the time in seconds. So express the kinetic energy of the ball as a function of time. So what do we need to kind of figure out for this question? Well, first thing we need to know is we need to know this kinetic energy equation. Again, what do we know from our question? Well, we know we have the mass, m, is 350 grams for the ball. And we know the velocity, the initial velocity, put a little I here for initial, so v with a little subscript I, is 40 meters per second. So what we need to do for this question is we need to show the kinetic energy of the ball. Well, here's the kinetic energy here, but as a function of time. So I'm putting a little 3 here because we know these and we know these, but we're ultimately trying to find this. So how does my equation change here then? Well, if this is my energy equation, I can now write this in terms of function of time. So I can do this in terms of velocity over time, or velocity and time. So just like kind of like we were learning function notation where we'll set the thing in the brackets here, then it'll change everything in the equation here. Well, we had k to v here, where v is just the v here. So now that we have k and then velocity here, it's going to be the same equation, but I'm going to replace the v now with v at t squared. So this is our equation as a function of time, but I also have to put the information in there. So what did we say is our velocity? Well, we have an equation here for that. So for part 5 here, I have to know my velocity is this. So I'm going to put the velocity equation into here. I get 0.5 m 40 minus 9.8 t squared. I can now put in the mass as well, which we said is 350 times this. And then I can just maybe multiply these in the front. So I get 0.175 and then 40 minus 9.8 t squared. So I could expand this if I wanted to, but again, if I'm given a t value here, well, for time, then I don't really need to expand it. I can just put it in here, follow BEDMAS, and get my answer. So therefore, our equation for here is going to be, in terms of time, 0.175, 40 minus 9.8 t squared. Now, so let's determine the rate of change of the kinetic energy of the ball at 3 seconds. So now that we know the kinetic energy of the ball here, in terms of time, is this. So if I want to find the rate of change of this kinetic energy, well, rate of change implies we have to find the derivative. So let's find the derivative of this. So which rules do we have to incorporate here? Well, I have a constant here, so it's not going to change much here, but I do have a power in the brackets here. So this is actually going to be our chain rule, or our power rule, because the power rule is just a more specific type of chain rule. So this is going to stay the same. I'm going to take my derivative of the outside here, bringing the 2 to the front, keeping the inside of the brackets the same. Subtract 1 from the exponent, we just have a 1 here. And then all of this times the derivative of the inside here, which is negative 9.8. So if we wanted to, we could arrange this like we did before. We had kind of f at x is equal to that thing outside the brackets, and then g at x was the 40 minus 9.8t. If I take the derivative, I get like 2 to the power of 1 here, then this has to be the same. And this one's just going to be negative 9.8t. That's if I found the derivative of these. Remember, this is just our chain rule here. So I'm just going to put that in here. This is our chain rule. So if you're not sure how we got this, double check what our chain rule is when we have an exponent like this. So now I have it like this. I have these numbers in the front that don't have really a variable, or they're kind of on their own. So I can just multiply these all together. I get k prime at t is equal to negative 3.43, then 40 minus 9.8t. And now we're just finding the kinetic energy of the ball at 3 seconds. So I'll set this at 3. Well, sorry, the rate of change of the kinetic energy of the ball at 3 seconds. So rate of change is important there. So 3.43 negative, 40 minus 9.8 times 3. I can simplify all of this. I get 40 minus 29.4, negative 3.43 times 10.6, and I get negative 36.36 joules per second. Or measure energy in joules. So if you took other science courses, you've probably seen joules before. So just a reminder for joules, I'm just going to put here K is equal to kinetic energy. That says energy. One more time. Energy, and we measure it in joules. There we go. So we measure kinetic energy in joules. And I'll write the therefore statement. Therefore, the rate of change of kinetic energy. Sometimes you might see like KE referring to kinetic energy, but I'll just write the whole word out here. Is negative 36.36 joules per second. And I want to make note that this negative in the front, what does this negative imply? Well, we said for a lot of our work, we have to kind of give a direction, but in this case, our negative is going to be the fact in terms of energy, we are losing energy, or the amount of energy is decreasing. Which makes sense because if you throw a ball upwards, you're throwing it with some energy, but as it goes up, there's less forces acting on it. It's going to lose some of that kinetic energy before it starts to fall back down again. So our negative means that the energy is being lost in that ball. So that's it for that last example. So try some of the homework, and thanks for your time.